Swayam Prabha. Digital India. Educated India.
We have seen earlier how to design a rotating system so that it is completely free from unbalanced forces and moments, resulting in a perfectly smooth operation. Now, we should discuss that given a rotor or a rotating system, how to balance it. Now, this balancing of existing rotors or rotating objects can be done in two ways. When the objects or the rotors concerned are small in dimension, they can be placed on some machines which we call as balancing machines. On the other hand, if the rotor and the rotating system is very large, like an alternator or some huge turbine rotor, so in such cases it is not possible to put these rotating objects on any machine for balancing purpose. So, we have to devise a technique for balancing those big rotors and big rotating objects in their original condition, original position. So, first we will take up the case of balancing machines. We will take up two types of machines. One, a very simple and rather crude version, which is called the pivoted carriage machine. The other is slightly more sophisticated and provides better accuracy, and that is called Gestalt balancing machine. The basic principles are very similar. So, first I will take up the simpler machine and explain the fundamental underlying principle which is used in all balancing machines. So, if we have a rotor, say our rotor is like this. This is a rotor which we would like to balance. It has been told before that we need two balancing masses to be placed at suitable angular positions at some two suitably chosen balancing planes. Then if everything is okay, the whole system will be absolutely free from unbalanced forces and moments. Now, the choice of balancing planes that depend on the construction of the actual rotor. Say for example, in this case it may be more convenient to select these planes as the balancing planes, because it is easier to either add a mass here or the same result can be achieved if some mass is scooped out or removed from a diametrically opposite position. The effect will be same as adding a mass here. So, therefore, these faces of the rotors may be chosen as the balancing planes, but anyhow this is just one particular case. So, it will depend on the situation. So, if we have a rotor like this rotor is placed on a carriage. The carriage has two half bearings. Now, what we do, we take a pivot to support one end of this carriage, and the other end is supported on a spring. Now, once this rotor starts rotating, then the centrifugal force or unbalanced inertia forces will start appearing depending on the speed of the rotor. Now, here we may assume that the complete unbalance of this rotor is represented by two masses, one in this plane and the other in this plane. Just it is our choice. Now, if that be the case, then if we say that this is some mass m1 and say some mass here m2, these two masses make complete representation of the total unbalanced situation of the rotor. So, now if we put the pivot on plane 1 or just under plane 1 and support the carriage by a spring at the other end, then this m2, which represents the unbalance of the rotor, and this mass m1, which represents the unbalance of the rotor and this plane, the effect of the unbalanced force produced by this will be nullified because this point is hinged. So, the motion, the rocking motion which will be generated the carriage will rock like this. You can imagine it will just rock like this with this as the pivot. Now, the effect of this unbalance will be completely gone. So, what is done that we then attach one trial mass on plane 2 and rotate its location gradually until that time when the amplitude of oscillation at a particular speed becomes minimum. So, that is the situation where we may consider that this trial mass is approximately opposite to the m2. You can see it can be explained this way. If m2 is this, then the location where mt2 will have minimum vibration produced will have to be here, diametrically opposite. Next thing what we have to do, that means at any other position the amount of m2's inertia force which this will neutralize will be lesser. Here it will be maximum effect. So, therefore, amplitude of oscillation will be minimum due to the unbalance created by m2. Next what we have to do, we have to gradually adjust mt2's magnitude or its radial position, because what actually matters is the eccentricity and the mass product. So, you can change the magnitude of the mass or vary its radial position, whatever may be the case. When you change this product gradually, until and unless this vibration almost stops. So, what we have done, we have completely neutralized the effect of M2 by putting a suitable balancing mass which has been adjusted to become the balancing mass. The original trial mass has been converted, so that this effect of M2 in creating unbalance is neutralized. Next, what we do, we just shift this pivot to the other balancing plane 2, and then what will happen, the oscillation and the spring is shifted here. So, when it is rotated, then the unbalance which is created by M2 will be having no effect, and unbalance created by M1 is going to have the effect, and we follow the same procedure in placing one balancing mass on this plane. So, we start with balancing or trial mass MT1. We first see that which angular position this produces minimum oscillation, and then we adjust the product MT1 and U1, so that the vibration almost vanishes. Now, of course, you may say that this is purely a very crude arrangement, because we are doing everything based on our visual senses and tactile senses, but it gives reasonably good performance or good results, and though the result or the result what we get here may not be perfect, or balancing may not be absolutely accurate. Now, the same principle can be applied in the machine here, Gishol type machine, only it is more sophisticated. So, I will explain the fundamental principle. So, here the disadvantage was some inertia of this carriage. So, that itself makes the whole operation somewhat inaccurate and less sensitive to the unbalance present in the rotor. If the unbalance present is very small, maybe it will be completely I think offset by the effect of the large inertia of the carriage, etc. So, in Gishol type machine, what is done? No carriage is used. Now, it is mounted on two bearings. And the bearings are supported by springs. So, we do not use any carriage, but we just place the whole rotor on just two light bearings which are supported by springs. Then what is done? The motion of this bearing is picked up by a solenoid, or rather it is connected to a solenoid which can then move along with the bearings, and there is some kind of an electromagnet or permanent magnet. Then this I am using green for the electrical circuit So, first let us understand the whole setup. As I was mentioning, these bearings which can move up and down supported by springs, either up and down or to and fro. It may be actually whole thing is actually in horizontal plane or maybe vertical plane. Then these solenoids also move up and down here. These are the electromagnets or rather permanent magnets. Then the coils here, they will generate, depending on this motion, some voltage. The amplitude of this voltage, which is an alternating one, will depend on the amplitude of this for a particular given frequency. Now, I think again if we now keep the same principle in mind, that the whole system's unbalance can be represented by or can be imagined to be represented by two unbalanced masses. So, now let us see, we know that the effect of this mass, if we ignore this effect of this mass to produce an unbalanced force here, will make this end oscillate at a larger amplitude. So, if somehow if we ignore this, then the oscillation of this rotor axis will move like this, and the voltage generated here will be more than the voltage generated here. Now, I think the ratio of the two voltages, because of this M2 only, here and here it is something fixed depending on the rotor's construction, etc. So, if we now adjust, that means this voltage here which is generated and this voltage which is generated, if we apply it here so that we adjust this in such a manner that this fraction of the voltage generated here is exactly equal to the fraction of the voltage generated here, then here what we will get is 0, because this voltage generated by here is suitably compensated by this voltage generated here, and the ratio of the two voltages, that is taken care of by this potentiometer arrangement. So, effectively this circuit will be now insensitive to any unbalance produced at this end. So, whatever this circuit, depending on the location of this potentiometer arrangement, it will now give whatever effect or voltage here comes is due to this M1, which is really present, though temporarily we imagine it to be absent, but it is present. So, now whenever this moves up and down and this voltage changes its direction, this stroboscope will flash for 1 microsecond as soon as the direction of the voltage or the sign of the voltage changes. So, it is arranged in such a way that when this is at the top position in its vibration, then it flashes. So, you can see the angular position, if it rotates at reasonably high speed, then flashing also will be reasonably high speed, and you can see the marking, there will be generally a protector kind of arrangement which will show you the angular position when this is at the highest or where M1 is the lowest. Now, if the damping in the system is less, very little, then what will happen? The motion will be in phase with the disturbing force, if the natural frequency is not above the normal frequency or the natural frequency, the forcing frequency is not above that. Similarly, if we have another circuit where we have compensated the voltage generated here due to this suitably, so that the voltage generated by this due to this effect is that circuit will produce the flashing only when this particular masses effect is concerned. So, thus depending on which circuit we are using, we can find out the angular position of this and angular position of this using the stroboscopic thing. And this can also tell us about the magnitude of the two unbalances present by suitable calibration. The basic principle will be then that you slowly adjust the magnitude of the mass or the magnitude of the product of the mass and its eccentricity in such a way that the result is minimized to 0. So, these are the principles of balancing machines which are used for balancing of actual rotors when they are not very large. Now, let us consider the case where the rotors are very large and you cannot bring them to your lab to put on balancing machines. It is like a turbine rotor or a huge industrial fan and so on. Such cases have to be tackled and balanced in their original position or in the field itself. That is why this technique which now I will present is called field balancing. It is very important, particularly for engineers who are working in the industry. First, I will discuss the case of balancing a disc. It is not only that the basic principle of this technique will be clearer with the help of this two-dimensional object, but in many circumstances the real thing may be approximated as a disc, like a huge industrial fan or blower which is in the form of thin blades. So, therefore, let us take the case of a disc balancing. Now, we will take up two cases. One is slightly advanced and sophisticated, which requires some instrumentation, and the other case which requires minimum instrumentation and can be done by almost anybody. So, the setup will be something like this. This is the disc on a shaft. The shaft is mounted on bearings. So, this is an oscilloscope which can measure two signals, double beam oscilloscope. The whole disc is shown here. This is this view from this side where you have taken this pickup. Now, this is a vibration pickup which picks up the vibration of this disc through some kind of a sensing. you can put this pickup on bearings or anywhere suitable position. Its main job is to measure the vibration signal. Then this shaft is also connected to a device which we call sine wave generator. Now, this signal and this signal, when they are taken to a double beam oscilloscope, what we will get? This will produce a sine wave, simple sine wave, and it is physically locked with this sine wave generator and the disc. They are locked because they are rigidly connected. So, the sine wave generated will depend on the rotation of this, or it is representing a rotation of this at its angular position. Whereas this will show the vibration of the disc because of the unbalance present, and when it rotates at some large speed or suitable large speed. So, now what will happen? Say sine wave generator, say for example, generates a sine wave. Continuously, and this pickup, say for example, it gives a vibration. Of course, remember, since in steady state situation the frequency of this vibration also will be same as the speed of rotation, because the vibration force or the exciting force is nothing but the centrifugal force generated by the rotation. So, they will have the same frequency, but they need not be at the same phase. So, what will happen? So, this will be pickup A and this will be pickup B. I will draw it in a slightly bigger way. So, this is the sine wave generator, and the signal which we are getting from the vibration pickup is given by this, and so on. So, therefore, this is what? This is nothing but the angle by which the signal of, or the vibration or signal of this is leading the sine wave generator. So, what we have got? Let us see what we have got, that we have taken the rotor in its own position, rotated it at a suitable speed omega to generate enough vibration which can be picked up, and then the signal which we have picked up is given by a sine wave whose magnitude is A and which is at an angle phi 1 from our reference. This is the reference now. So, I can draw it with the help of a rotating vector, because any harmonic function of time can be represented by a rotating vector when we consider only the component of that vector, rotating vector, as the real quantity. So, if this is a vector A rotating with a speed omega, then at any instant this is omega t and its magnitude is simply A cosine omega t. So, a harmonic function of time. So, we will just represent the vibration when it is rotated at speed omega by A1. Now, A1's magnitude is this, and its location from this reference is this. Where this angle is phi 1. Next what we do, we attach at some suitable location a trial mass. At an eccentricity Et. Again we rotate the whole system at the same speed omega, and we get another signal which we call A2, whose magnitude is this much, and it has a phase lead with our same reference, because this attachment we have not changed. So, whatever this generates is actually physically connected to the whole physical system. So, now we get another signal which is also a harmonic function of time, and therefore can be represented by another rotating vector A2, where this angle is phi 2. Okay. So, now what we have got? We have rotated the rotor or the disc at some suitable speed to produce measurable vibration, and the vibration what we get is represented by a rotating vector of magnitude A1. Then we attach a trial mass MTET and rotate the system at the same speed omega, and we get again the vibration as A2, which is at a different angle from the reference phi 2. Now, what is this quantity? I am representing this bar over the number to indicate that they are vector quantities. Now, this is this A2 minus A1. Originally, without any trial mass, we had this vibration. With trial mass, we have this vibration. So, the original vibration plus this becomes the final. So, this is nothing but the effect of the trial mass. So, now where to put our balancing mass so that the vibration which is produced by its original unbalance is completely gone? Now, you can see that if we rotate this effect of MTET in this direction by this angle phi, so that it matches with the original vibrations direction, this vector, and its magnitude is increased or changed in such a manner that this length and this length equal, then what will happen? If we rotate this by an angle phi and put our balancing mass MBEB here, and MBEB is such the magnitude of the one vector by the magnitude of then what will happen? Then this MBEB, its effect will completely neutralize the effect of the original unbalance, and the vibration produced in the system will be 0. So, this is the technique which we can use for balancing disc like objects. Now, here of course, we can also treat the whole thing as a vector 1. If we take MT ET as a vector quantity in this way, and MB EB, always this product is important, by another complex quantity like this, and delta as another vector or complex quantity then MB EB vector we can say is delta multiplied by MT ET vector, so that delta into MT ET magnitude is equal to, that means, or I think we should say not that way, that delta we are using as an operator, which will be later when we very useful the concept when we go for rotor balancing. Actually for disk balancing this is perfectly all right, but you can see that operating one vector by another vector, what it does, it changes its magnitude by taking the product of the two magnitudes. That means the product, the magnitude of MB EB will be magnitude of delta into magnitude of MT ET. Similarly, the phase or the angular position will be just added. Phi MB will be phi MT plus phi delta. So, and magnitude of delta and value of phi, this can be found out just as I mentioned here. We will discuss this at a later stage when we take up rotor balancing in the next class. Here we do not need that complex notation as much, because this is quite simple and clear this way. Now sometimes one may find a situation where you will find that you do not have a sine wave generator and a double beam oscilloscope. What you may have in industry is simply a vibrometer which can measure the amplitude of vibration, nothing else. Even with that kind of a simple instrumentation we can do field balancing, which I will tell now. So now we will take up the case where we have a simple vibration pickup, where you can get the amplitude of vibration, that is all, nothing else. We do not need the sine wave generator or any kind of complicated instrumentation like a double beam oscilloscope. What we do now, we take the disc, rotate at a suitable RPM or suitable speed omega, and measure the vibration amplitude A, we call it A1. So therefore, run the disc at speed omega, that gives vibration A1, magnitude, amplitude only, we cannot have any phase or anything like that now. Then what we do, we attach a trial mass at any suitable location and run the system at the same speed. Then this will give a vibration amplitude A2. Attach MT at the diametrically opposite location. and run at omega. This will give a better way of whole thing. Maybe if we try to match this one and this, it is possible to do like this. If you want to have that, it is possible that we call it a 0. Since it is 1, we call it a 1, opposite location 2, and we call it a 2. So, this is location 1, this is location 2, now you see very interesting thing. A1 is the A0 is the amplitude of vibration without any attached mass. A1 is the amplitude of vibration when a mass mt is attached at location 1. Similarly, A2 is the amplitude of vibration when the same attached mass is shifted to a diametrically opposite position. From these three quantities, we get lot of information. Let us see. So, if the vibration is due to the original unbalance is say A0, and say the effect of mt in location 1 is this, then A1 will be this. When we place it in the diametrically opposite position, then obviously the effect of the trial mass will have to be opposite to this, and A2 will be this. So, just getting these three quantities, it is possible to have this diagram. How we do it is we draw a triangle whose one side is 2A0, one side is A1, other side is A2. So, this triangle we can always draw, and as you can see that this is equal to this is equal to this, then this A2 is equal to this A2. And if we draw this triangle 2A0, A1, A2, then we know this is the effect of the trial mass in its position 1. So, we know that how much it has to be rotated and in which direction. So, therefore, the actual position of this trial mass will have to be somewhere here, balancing mass. You have to rotate in the same sense by same angle phi to nullify the effect of the original unbalance, and you have to of course change the magnitude also. Mb will be equal to mt into magnitude of A0 by magnitude of A1 minus A0. Since A1, A0 they are known and phi is drawn through this diagram, that means I draw a triangle 2A0, A1 and A2. Moment you do that, the midpoint if we join, this becomes phi. So, phi is known from this diagram, and magnitude of the balancing mass required to nullify the or neutralize the effect of the original unbalance we get here. This is okay, but there is only one snag. that when I draw a triangle like this, I can draw the triangle like this also. Then the same angle phi which I will get here, that indicates that the location of the balancing mass will be at an angle phi, but in the clockwise direction. So there are two possibilities, which is the correct one. To do that, what we propose to do is that we locate the trial mass, we make a third attempt. The same trial mass we locate at a position which is at right angles to the position 1 and position 2 like this. That means rotated by 90 degrees in the clockwise direction. And then so attach MT at location 3 at 90 degrees and run at omega, and now you get A3, the amplitude of vibration we get A3. So here you will find that we can show, now it is possible to, with this data it is possible to distinguish between the two. Say if this is the situation, then when you have, this is the position effect of the trial mass in position 1, then what will be the effect of position or the trial mass at 90 degrees? When rotated by 90 degrees in the clockwise direction or anti-clockwise direction, as we have done it here, you have seen that we have rotated in the anti-clockwise direction 90 degrees. So the effect also will be shifted by 90 degrees this way, and resultant effect will be finally A3. On the other hand, if this is the situation, this is the original effect A0 and this is the effect of MT at location 1, then if you rotate this by 90 degrees, the effect of MT in the anti-clockwise direction, this would have been the effect of the trial mass in position 3 and your A3 would have been this. So considering that whether your A3 is large or A3 is a small quantity, you can find out whether the configuration will be this or configuration will be this. So this third way, the trial will, third run will be essential to identify the two or identify the correct configuration. So you can see here that we don't need any sophisticated instrumentation, we only need a vibration pickup to give you only the amplitude of vibration, then run the system at some suitable speed so that you get measurable vibration and the amplitude is A0. Then at some suitable location you attach a trial mass MT and run at the same speed, get an amplitude of vibration A1. Then rotate this by 180 degrees, that means take it to the diametrically opposite position, run at speed omega, you get amplitude of vibration A2, and before that you can also rotate it by 90 degrees and a third location you can choose to put your MT and run this system at same speed omega will give you amplitude of oscillation A3, amplitude of vibration A3. With that you can draw the figure, it will be either this or that depending on what is the magnitude of A3. If it is large, that is the configuration, and then you have to rotate your trial mass in the clockwise direction by an angle phi, magnitude will remain or it will be given by the same relationship, but at least the position will be different, it will be here. This is the second case. Actually you have to place it here and its magnitude will be suitably scaled according to that equation. But if it is A3 is small, then your location will be this, and this will be your phi. So, this is the way we handle the field balancing problems of disk-like objects. Disk-like object means most of the matter is considered to be confined to a plane which is perpendicular to the axis of rotation. Now, I think in the next session we will extend this technique of disk-like objects for finding out the balancing mass required by some experiments in the field in its own position for rotors. Like that is a very major problem. A large number of systems are actually extremely critical from this point of view of balancing, like alternators, turbines and so on, where they are very heavy and they have to be balanced in their original position.